Hello and welcome back to the Astro Imaging channel. Tonight's session is on the basics of statistics for astro imaging, and John Hayes is back to present on that. But as always, we're going to jump into our image of the week, and today's image of the week goes to Phil Kaiser, and it is Coddington's Nebula. I'm going to make sure you guys are seeing the same thing I am. Yes, Coddington's Nebula. And Coddington's Nebula is actually a galaxy, and you can see it here surrounded by the IFN. Really a great image. You might have seen it pop up previously, but definitely just, I don't know, an awesome image. Sometimes these kind of diffuse galaxies are hard to make look good. Well, Phil figured out the way. Just a really cool looking image, but of course, Phil hadn't been able to come in today. So if he ever wants to comment on it, he's welcome to jump in or post something about it. But for now, we're going to jump right into the presentation. I'm going to hand it right over to John, who's in the room working off a secondary internet. But John, there you are. I'm handing it right over to you.
Okay, that's great, Adam. And let's see if we can get my slides up on the screen here. Let me just see. Got to share my screen here. We practiced this earlier. Let's see if I can get. Whoops.
Full screen. Use full screen.
Where is that? Is that up in the upper left? Where
upper left screen share. The green monitor with the white arrow.
Oh, there we go. There we go. And tell me if you don't see a full screen here when I pull this up. Let's see if I can. Get this going here. Let's try that. And you should see a full screen there that says Basic Statistics for Astrophotographers. Do you see that?
I do not yet.
Gee, we tried this earlier. My son and I set up a Hangout. We tried it and it worked flawlessly. So let's see. I am sharing the screen. And let's see. Desktop. There it is. Oh, here. Let's try this.
There you go.
And let's see if you see that.
Yep.
Now, do you see that?
Yes.
Okay, good. All right. Well, when you guys invited me to do this, you know, the original idea was to go over some basic statistics for folks who do astrophotography. And of course, statistics is a pretty big subject. And so I paced the floor a little bit, and I thought, gee, we really want to limit this a little bit to the things that we use as astrophotographers and to explain some of the basics that we use when we do astrophotography. And so one of the things that I want to start out with is just to state right up front that understanding statistics is really essential for astrophotography. Every image that we record is a signal plus some noise. And just so we're clear, signal is the information that we want to record. And ultimately, this is image detail. That's the desired signal that we have. We also have some undesired signal that will be present, and this can come in the form of stray lights, your neighbor's street light, or cosmic rays, or dark current, bias current, those kinds of things. And we're going to remove that through calibration and filtering, and we'll talk a little bit about that stuff. But the next thing we want to worry about is noise, and noise is the variation in the signal that makes us less certain of the information that the data contains. And in the case of imaging, noise obscures image detail, and so we really want to minimize noise and maximize signal. And we can manipulate the statistics to improve this ratio that we call signal to noise ratio. And that's our ultimate goal, is to maximize the ratio of the signal to the noise by maximizing signal and minimizing noise. The thing that really makes this possible are linear sensors. Back when in the 60s, when I started doing astrophotography for the first time, we used film, and film is inherently nonlinear, and it's got a lot of problems. But when CCDs, digital CCDs came along, it really changed everything in terms of astrophotography. These things were invented back in 1969 at Bell Labs by these two guys, Smith and Boyle. The very first one was a 100 by 100 CCD that appeared in 1975, and just as an interesting side note, at my first company, we built one of the very first digital cameras using this very same sensor to do optical interferometry. And we were such dummies, we thought this was so great for interferometry, we didn't realize that the much bigger market was building cameras, and that's really what we should have done. But we had so much fun testing optics with this thing that it didn't occur to us to sell them as cameras. But the first digital cameras appeared kind of in the early 90s. And I don't know if everybody realizes it, but 2009, rather, the Nobel Prize was awarded to Smith and Boyle for the invention of the CCD. So it's a Nobel Prize winning invention. It really has had a major impact on the world. And the thing that makes it so good for us who are doing astrophotography is the fact that it has a linear response. So if we double the signal, we get double the response. That's kind of the basics of what a linear response means.
John,
yes.
Can I interrupt you? We see your entire PowerPoint program. We don't see the slides. Are you seeing the slides?
Oh, you don't?
No. Let's try.
That's bad. This happened last time. So you don't see my screen. So what is it? Yeah.
I see your screen, but for some reason I don't think the full screen is working properly.
Yeah, it's very odd. So do you see the PowerPoint? What do you see?
I see PowerPoint. I see the proper slide, but I don't see a full screen. So you're working your way through the Powerpoint.
Okay, are you
not seeing the PowerPoint move at all? Actually, just seeing your title slide.
Oh, that's bad. Oh, so
are you actually playing the PowerPoint, or are you just?
Absolutely. Yes, I am. Yeah.
And which monitor are you playing it to? The same one that you're looking at?
That's right, yeah. I'm just playing this is really frustrating. This happened last time I was on, and we had a real trouble getting this thing to work. Let me go back up here and see if I can go back to screen sharing, Google Hangouts. Let's try, it says desktop. Let's try this. And let's just see if this will work.
That works.
See if you can.
That works.
And you see, and now do you see the second slide?
Yes, we see the slides, but we don't see it in presentation mode, if that's what it's called.
Okay, well, let's try here comes presentation mode. Let's just try this and see if you see this. Here I need to, actually I'm having a little trouble here. There we go. So let's try this. Now, do you see the full screen that says understanding statistics is essential?
Now you got it.
You do, okay. Okay, so now we've already talked about this a little bit in terms of signal and noise. And where I am right now is talking about linear sensors. And do you see that slide?
Yes, we do.
Okay, good. All right. And you should be able to see my cursor there. And so anyway, so where we are here is talking about linear response. Double signal equals double response. And so what these linear sensors allow us to do is to do image calibration. And to do digital processing, which we all do when we're doing astrophotography. And it turns out that when we use statistical processing methods, we can greatly improve our signal to noise. And in the early days of CCDs, astronomy was a very early application. And in fact, it was one of the bigger applications in the early days. We all know today that it's a tiny application. Hardly anybody pays attention to us doing astrophotography. But in the early days, this was a big thing. The astronomers recognized the value of having a linear sensor. And it's really what allows us to use digital processing to create these high-quality images. And you should see the problem is photons usually don't arrive uniformly. Does everybody see that? Slide number 4.
Yes, we do.
Okay, just checking. I want to make sure we're all on the same page. So this is the problem, is that when photons come out of the sky, when we're pointed at some object, we don't get photons arriving uniformly. I think when we start out as beginners, we think we're going to just point our camera at an object, and it's going to be like doing normal photography. We're going to see this very uniform signal. All of our little buckets that catch these photons raining down are going to fill up to an equal level, and everything's going to be good. And if they did, there'd be no noise, and we wouldn't care much about statistics at all. But the reality is we have this thing called shot noise, which is the noise inherent in the way photons come down. And what we're trying to record is a very faint signal. And of course, the light that's coming down and being collected by our telescope is composed of discrete packets called photons. And you guys all know what they are, that shorter wavelengths the blue photons have more energy than the longer photons, the red ones. And they arrive in a statistically random way. And in fact, they arrive just exactly like raindrops. The statistics that govern the way photons come down is exactly the same as the way raindrops fall. And in fact, one day I was walking with some folks from a telescope manufacturer, and we were walking into their building, and there on the concrete were raindrops falling. And I said to them, look at that, that's just like photons coming down. And they were stunned. They had no idea that was true, which kind of surprised me. So I want to make sure everybody understands this, that photons come raining down, and we have all these, if we put out our little buckets, each one of these buckets is going to collect a different number of photons, and that's going to create a variation in our signal. And I love this diagram, and I just had to use it. It comes from Nikon, and it talks a little bit, it shows a little bit the way a CCD works, and they even use this concept up at the top of raindrops coming down. And of course, these raindrops are really just photons being collected by all these buckets on all these conveyor belts. And really, the number of photons and the number of photons per unit area that are striking the focal plane, which is where these buckets are, is determined by something we call radiometry. And we're not going to go into that in this talk of how we determine how many raindrops are really falling per unit bucket here. We're just going to say we've put some buckets out. We're going to assume that the quantum efficiency is 100%. In other words, each bucket collects every raindrop that hits it. And as they fill up, we're going to then take and we're going to move these buckets over on a conveyor belt. We're going to dump them into a shift register, and the shift register is going to measure and calibrate each bucket as it comes out. As we've said, if each sensor was evenly illuminated, the photon statistics mean that each bucket will contain a different number of photoelectrons. And so that's the problem that we all face, and you guys all know this. We're taking pictures. And this may be a little bit hard. I hope you can see this on your screen. But I've simulated here the effect of shot noise. And this is just photon noise, no other sources of noise. But if we start out with n photons and we go to 4n photons, 8n photons, you can begin to see that the image gets cleaner and cleaner until we get to what I call an infinite number of photons. It's really just a very, very large number of photons. The noise begins to decrease. That graininess that you see in the unevenly filled buckets across the image begins to decrease. Now, of course, when we have very few photons, it'll be a fainter image. So I've kind of normalized out all the intensity of each display here. I haven't tried to simulate how dim this would actually be compared to having an infinite number of photons, which would be infinitely bright. So you have to notice that with shot noise, the brighter parts of the signal are going to be cleaner. You're going to have more noise in those brighter parts, but it turns out that the signal to noise is also higher, so the image is going to appear cleaner in the bright areas. The dimmer parts are going to appear to be noisier. There's less noise, but they have a lower signal-to-noise ratio. So the effect of shot noise is that it varies across the image, and it depends on the brightness of the image. So the darker areas are noisier than the brighter areas. So shot noise is a spatially dependent noise, and I think everybody who's processed an astro image knows that. In the dark areas, it's a lot harder to process out the noise than it is in the bright areas. Well, let's talk a little bit about how the photons arrive. And the photons arrive and obey the mathematical relationship developed by Poisson. Simeon Denis Poisson in 1837 developed this. And he worked out the probability of n discrete random events occurring within some interval. And it turns out that what he worked out, and he worked it out, as I recall, for looking at how many people died in a hospital or something per unit time. And he figured out, he was a physicist and mathematician, and somebody had asked him to do this. And he sat down and thought about it, and he's a pretty smart guy, and he came up with this relationship. And it also describes the probability of n photons arriving per unit area per time interval. And just interestingly, I have to point out, he's the very same physicist who brilliantly predicted the Poisson spot, which was named after him, while trying to disprove the wave theory of light. You know, it's one of those brilliant blunders that he was very smart in a lot of things, but he didn't believe in the wave theory of light. And he said, he actually made a very famous argument to I forget who it was, Fermat or somebody, saying, you know, if the wave theory was correct, you'd see a little white spot behind a dark disk, and that's of course absurd. Well, of course he was right. It is there. The conditions for the Poisson distribution are important to understand. First of all, the events have to happen at a constant rate. They can't kind of come and go. They're operating at a constant rate, and that, of course, applies to the photons coming from a distant celestial object. We have to know the long-term average of the number of photons coming down. So that's something that we assume we know. Each event is random and unrelated to the other. So these are uncorrelated events. So it will work very well for things like photons, where the arrival of one photon doesn't affect the arrival of another photon. There are other ways to describe correlated events, and we're not going to even talk about that. I just want to mention that there are lots of different distributions and ways to handle correlated events and stuff. That's kind of beyond what we're going to talk about. We're going to talk about the simplest thing here. And then we're going to assume that the probability of an event occurring within any interval is proportional to the interval length. So if we double the interval length, we double the probability of having an event occur. So that's a basic part of deriving the Poisson distribution. Now I'm going to disappoint you guys if you wanted to see how the Poisson distribution is derived, and I'm going to put it off on. I'm going to give you a shameless plug here for the Khan Academy. For any of you who haven't done the Khan Academy, Sal Khan is just one of the best educators and the best guy I know of to explain things. And if you go to the Khan Academy and you type in Poisson distribution, Sal Khan gives a wonderful derivation. He does it right off the top of his head, and it's just brilliant. I will never do it as well as he does, and so I figure I'm not even going to try here. I'm going to explain the results of the Poisson distribution, but if you want to see how it's derived and where it comes from, it takes a little bit of calculus and some things. But he explains it so well, and I have to say, for all you guys here, if you haven't done anything on the Khan Academy, I very highly recommend it. I don't come on here very often or ever try and make an ad, but this is such a good thing. There are thousands of things on here, little subjects. There are 10 minutes each. I highly recommend, if you haven't visited the Khan Academy, to check it out. And what Sal Khan derives is this crazy-looking relationship up here of P of capital X equals K. Capital X is what's called a random variable, and it could be a variable such as how many photons arrive in 1 square centimeter per second is equal to the number of events that we have. So in other words, if we said the number per square centimeter in 1 second is equal to 5, then we can calculate, knowing the mean, and the mean we've designated with the Greek letter mu, and it's done by this relationship. It's mu to the kth power e to the minus mu over k factorial. And if you don't remember, k factorial is just k times k minus 1 times k minus 2 all the way down to 2. And you just multiply all those numbers together to get k factorial. And I'll do one of those for you in a minute. But you can see what I've done here is I've plotted the probability function for a number of different averages. And this first one in blue is for an average, I think, of 5. Yeah, it's 5 here. The next one is for 15. The next one's for 30, 45, 60, and we get all the way out to 75 here. 90 just starts to come up. Barely see it. But there's 75 in the sort of orange line. And you can see a couple things that happen. This is a probability distribution for discrete events. In other words, the event has to be 1 or 2 or 3 or 4 discrete photons arriving per square centimeter in 1 second. So these things enclose a lot of events, and the bigger the average is, the more events they enclose, and the wider they have to get. And the total probability is the sum of all of these things, and it has to add up to 1. And so the probability of all of the photons arriving in 1 second, all the possible photons, has to be equal to 1. And so that's why these go to a lower and lower amplitude and get broader and broader as the average gets bigger. So how do you read this thing? And I've kind of described that, and I want you to remember the Poisson distribution is discrete. In other words, it describes a discrete number of events. You can't figure out with the Poisson distribution when 2.5 photons are going to arrive, because you can't have 2.5 photons. The probability is up the left axis, okay? And it's the chance that you'll get any single result shown for any possibility shown by a single bar. So if I were to pick 11 here, for example, I could come up and I could read this off, and I could say, well, it's a probability of about 7.5% or so, whatever that is. Now, not quite, 6.7% is the probability of having 11 of these arrive. If I wanted to know what the probability is for catching a range of, say, 10 to 20 photons per second in that same square area, then I just simply add all these up for each of these bars. And I did it for 10 to 20, and it comes out, if you want to say that the probability of catching, say, 10 to 20 photons in that area when only, in this case, 15 are arriving per second, is 87.4%. So it's pretty high that you'll get that number of photons if the average is 15. So you can use this little equation, and again, if on average 5 photons arrive every second, what's the probability that 5 will arrive in 1 second? Well, again, it's just reading the chart or plugging in the numbers. And we just set k equal to 5, exactly 5 photons arrive. And remember, k factorial is k times k minus 1 times k minus 2 all the way down to 2. So 5 factorial would be 5 times 4 times 3 times 2 is 120. That's what that is for k equal to 5. If the mean is 5, this is 5 raised to the 5th power. And then you can just calculate e to the minus 5th. And you just do this on your calculator and calculate 17.5% for exactly 5 photons arriving in 1 second. What's the probability that 7 photons will arrive? Well, you can do exactly the same thing. Just plug in your numbers for k equals 7, you'll get 10.4%. That's how you use this thing. If we were to do something a little bit more, a little bit different, we could say, what's the probability that exactly 30 photons now will arrive in 6 seconds instead of 1 second? Say we go out to 6 seconds. Well, remember, the probability is proportional to the time interval. So if 30 will arrive in 6 seconds, well, that's 6 times 5 is, we can go out to an average of 30 now, and we look at k equals 30 in 6 seconds, then we can just plug those numbers back in here. We get 7.26% that will get 30 photons arriving in 6 seconds. Now, do you really have to know any of this to do astrophotography? No, not at all. I mean, you don't have to know any of this, but it's nice to know a little bit about what's behind the Poisson distribution and how do you read it. And that's what this is really aimed at, is just showing you how do you figure out what a Poisson distribution does. Well, you've got all these possibilities, so how do we know what's the real value? Well, here's the kicker. When we do astrophotography, we are really seeing the effects of quantum mechanics. So we're dealing with a quantum mechanical system, and there's uncertainty in everything we measure, and this is one of the outcomes of quantum mechanics. And astrophotography really makes this uncertainty very visible. We don't normally see the effects of quantum systems very easily in most of the things we do, but astrophotography is a special thing that allows us to see that. So what we do, if we want to know what is the real value, what we do is we assign the long-term average value to be the signal we want to measure. And that's, that just makes sense. If we were to integrate long enough, we're going to have some average value. So we say that's the signal. And we assign the spread in that signal to be the uncertainty in what we measure. Okay? And we call that uncertainty noise because it obscures the information that we want to measure. But it's important to understand that when we're measuring something, we call this photon noise, but it's really uncertainty in the thing that we're trying to measure. So how do we handle that uncertainty? Well, we express the measurement results within an agreed upon confidence level. And so the best way is to tie the confidence level to the known spread in the data. So in other words, we might say we measured this average, and I should have probably put a little bar over that x, that's the average, to plus or minus the uncertainty. I've just designated that here as delta x, is the uncertainty in the data set. And we define the signal-to-noise ratio to be the signal, which is just the average, capital X here, and again, I should have put a bar over that, as capital X bar over the uncertainty delta x. Well, what do we use for delta x? And this is where the concept of 1 sigma comes in. And we've all talked about 1 sigma, but let's talk about what is 1 sigma. Well, 1 sigma is something that we can use to measure the width of this probability distribution. And as I said, these Poisson distributions, depending on what the average is, they get wider and wider as we get more data, okay? And we saw that in the plot. So the uncertainty, the width of that probability distribution relates to the uncertainty. And so one way we can describe uncertainty is with something we call the variance. And the variance is kind of intuitively obvious. It's maybe not the most obvious one, but I'm going to talk about the variance as being a very obvious one. And it describes such a quantity. And the way we do this is we say, let's take the mean and we'll subtract any value we get from the mean. And we don't want to have sign be a problem here. So we're just going to square it because we know squaring things makes everything positive. And we'll just take the average of this thing. So take this thing, which is the square of the difference of the means, and take the average. And so this generates something that we call the average of the square deviation, and we call this thing the variance. The big problem with the variance is that the units don't match the original data because we did this squaring operation. Well, we can fix that. If we take the square root of the variance, okay, just take the square root of it, look at this. We get the right units. We get this thing that looks like this, and this is what we call sigma. And this is the root mean square. And I love calling it the root mean square because I can always remember how it's calculated. It's the square root, there it is, of the mean, which is this part of it, of the squares. I'm just taking the squares of the difference. That's what RMS tells you. And we call it 1 sigma simply because mathematicians, statisticians have forever used the Greek symbol sigma to designate this thing called the RMS. So RMS and sigma are exactly the same thing. It has the same units of the data as the data, and as we'll see, when we apply this to our distribution, it provides about a 68.3% confidence level, a little more than 50%, so 68% confidence level that our data lies near the average. Well, we can, now that we've defined this thing, we know what the average is. You guys all know what the average is. We do that all the time. It's just the mean, and that's where we take the data sets, we divide by n over the entire data set. That forms the mean. And we want to make sure we measure that over a large sample, by the way, for the Poisson distribution. Remember, we started out with the Poisson distribution saying that we know what the mean, the long-term mean is in the first place. And that's how we derive it. And when Sal Khan goes through this, that's an important thing. You got to know what that is, but you have to do that over a large sample. With photons, that's normally not too hard, unless the subject's really, really faint. But that's not too hard. The variance, we know what that is. Well, the variance, if we were to calculate this, and I'm not going to try and derive this for you guys. I think I'd put you all to sleep. But the variance for the Poisson distribution, if you work it out, turns out to be exactly equal to the mean, which is kind of magical. It's kind of a cool thing for the Poisson distribution. And if we do the same thing for the standard deviation, we take the square root, well, it's just the square root of the mean, which is a really magical property of the Poisson distribution. So we can calculate from a Poisson distribution what the signal to noise is. And as we said, this signal that we talk about is just the average, which is mu. We called that mu. And the noise, we just figured it out. The width, which is kind of the single 1 sigma width, is just 1 over the square root of, it's the square root of the mean. If we reduce this down, it just equals the square root of the mean, is the signal to noise. So this, again, is where the noise contribution is considered to be 1 standard deviation. And remember, that's not the full width. I mean, data could come in outside of that. But we like to say that this is our signal to noise level where we're confident to that signal to noise level to within, say, 1 sigma or 68% for that confidence level for some large value of k. And by the way, this is important for a large value of k. For large values of k, and this is where you get the 68%, the Poisson distribution converges to something we call the Gaussian distribution, where it has the same spread, the same width as the Poisson distribution. We'll look at what that means in just a minute. But I want you to remember the most important thing for a Poisson distribution, which again dictates the way photons come down, is the signal to noise is just the square root of the mean. And that's a really important thing that helps us. This is what allows us to do astrophotography and to get such wonderful images, that one equation. So what it says is that if we double the number of photons in, say by doubling the exposure time, the signal goes up by a factor of 2, but the noise only increases by 1 over the square root of 2. So that improves the signal to noise by a factor of square root of 2, which is 1.41. So if we were to plot for the average number of photons that we get, what happens to the signal to noise? You can see in this plot that it gets bigger and bigger. The more photons we collect, the higher the signal to noise gets as a function of time. Now it starts to get to a point up here with diminishing returns, and we'll come back to that in a little while. There are other signals that contribute noise. We've only talked about photon noise at this point. And you know, the photon noise point, I just want to add that that's a very important thing. Somebody was talking to me the other day about these guys doing very short exposures, very, very short exposures, and using only these short exposures to make an image. And they said, well, gee, we don't have to worry about going so long. And I said, no, you're still battling photon statistics. Now I want to make sure you guys are still there. Can you still hear me?
Yes, we can.
Okay, I want to make sure we are there. So, because if my connection drops out, I'll be talking to myself. so we'll check in with you every once in a while.
Okay.
So let's talk about some other signals that can contribute noise. First of all, is dark current. This is a thermally dependent fixed pattern signal within the sensor. Okay, cooling reduces the dark current. Cooling the sensor reduces the magnitude of this signal. And it also, because it reduces the magnitude, remember the magnitude is related to the average, it also decreases the noise. Dark current contains thermal noise. It's called Johnson noise when you hear people talk about that. It's caused by atoms kind of banging around within the sensor lattice. They can knock loose photoelectrons that obey Poisson statistics and look just like they came from photons. Okay? It is spatially dependent noise because it varies with position depending on the sensor, not on the image itself. Okay? So dark current rather, is spatially dependent, not heavily spatially dependent, but you do see structure to it. Other sources of noise, read noise, like which includes 1 over F noise, conversion noise, amplifier noise, and a bunch of other stuff in there. That all injects noise with Poisson statistics. And these add noise uniformly over the whole image. They're spatially independent noise. In the end, you really can't tell where any of this stuff comes from. But you can estimate the effect of combining all these sources of noise, and we'll look at that shortly. I mentioned that for large values of k, large samples, the Poisson distribution converges to the Gaussian distribution. This guy Gauss figured this out from the binomial distribution. There's a whole history behind this, but again, I'm not trying to teach you guys all about statistics here, probably half because I'm not a super expert on it, but also because it's complicated and maybe not so relevant. But the Gaussian distribution turns out to be super useful and very, very common in almost all areas of science, and certainly within our hobby of astrophotography. It's also called the normal distribution, the bell curve. It becomes very close to the Gaussian distribution when the average is greater than around 30 samples or so. I mean, plus or minus some, but it's somewhere around 30. You can kind of wave your hands at that. It describes the probability density function of uncorrelated random events on a continuous basis. So these are no longer discrete events. You could have half an event happening or half of something happening. And basically, the relationship for the Gaussian distribution looks like this. This normalizing factor out here makes sure that if you integrate under this curve, you end up with a probability of 1. The total area under the curve has to be 1. The important part is this e to the minus u minus the mean squared over 2 times sigma squared. And again, one of the things that you have to understand about the Gaussian distribution that's very different than the Poisson distribution is that you can't take the value off of the Gaussian distribution to determine the probability of one single event. Because this is a continuous curve, you always have to find the probability of events between 2 extremes. I call them x1 and x2 here. But you calculate the area under the curve. And this has to be done numerically, by the way, because there is no analytic solution for the area under the Gaussian curve. But the total area under the curve from minus infinity to plus infinity has to come out to 100% probability. And if we look at what the Gaussian looks like, and I just did these with zero mean, you can see Gaussians for different standard deviations, 1, 2, 3, and 4. And again, you see that the amplitude gets smaller as the curve gets wider. And I also want to emphasize that if I were to pick the probability of an event happening at exactly, let's pick 1 standard deviation, it's somewhere out here. I hope you can see my cursor there. But if it's occurring right there, we can't really tell what that probability is here. We could say, remember, the width here would be infinitely small for 1 event there. So we have to always go between 2 limits here and integrate under the curve, and that's why this is called a density function. And what we can find, what statisticians have done, and it's easy to do if you're good with Excel, is you can sit down and you can plot this curve, and you can look at the area under the curves. And this is a little table showing you standard deviations from the mean and fraction of events that lie within the standard deviation of the mean. So if we were to say plus or minus 1 sigma, and this is what we've been talking about all along, there's that 68.3%. 68.3% of the events will occur in plus or minus 1 sigma range. For 2 sigmas, we get all the way up to 95.4. 3 sigmas, plus or minus 3 sigmas, gets us to 99.63%. It's pretty good. I used to work with folks who did high volume manufacturing, and they talk about plus or minus 6 sigma. And the reason is they have so many things that can go wrong that you want to have probabilities that are out to 6 or 7 places of 0.99, 0.9999999%, or the probability of failure in the thing you're trying to make gets to be pretty high. So we used to have to qualify our equipment to plus or minus 6 sigma, and you can see even 5 sigma here is 4 nines past the decimal point. It's pretty darn accurate. It's pretty inclusive of just about all of the data. So if we're talking about 6 sigma, that's pretty close to 1. With regard to the probability and the Gaussian distribution or even samples, the things we want to try to make sure we know what they are. The mean is just simply the average. You guys know what this is. We talked about it a bunch. The median is the value where half of the data lies above and half of the data lies below the median value. And so the probability of events above the median are equal to those below the median. And for large sets of random data, the median is equal to the mean, okay, if we get a large enough event. But if a large enough set of data. But for smaller sets of data, or for data that is not does not have a Gaussian distribution, the median may not be equal to the mean. And noise can really help drive the mean from being different than the median. So it turns out to be very useful for removing outliers with a digital filter. And we'll talk very briefly about digital filters shortly. The mode is the value that occurs the most often. It's only valid for discrete sets, and it might not exist, and really we don't use the mode very much, but you might see somebody talking about the mode. Let's talk very quickly about weighted averages. A weighted average is pretty much it's very similar to an average, except that we weight each value by some number. Here I've called it W sub I. So we take the values that we have, multiply by a weighting factor, and take the average of those. But we have to require that the sum of the weights is equal to 1 when we formulate this weighted average this way. And you might say, well, what good is that? Well, it turns out a weighted average is, first of all, it's very good for calculating things like center of gravity. It's also really good for minimizing noise using inverse variance weighting. And Pixel Insight actually has this in their stacking option. So it turns out if you set the weight to be 1 over the variance times some constant, we need that constant to make sure that we satisfy this relationship that the sum of the weights equals 1. And if we set the constant to be 1 over the sum of the variances, we satisfy that condition. So if we simply weight our images as 1 over the variance, okay, noisier data will have a lower weight and hence less effect on the result. And that's a really useful result when you're stacking your data. So just understanding when Pixel Insight says, do you want to use a weighted average as one of the options when you do your stacking, that's a very good thing to check, because it makes sure that if Pixel Insight detects one of your images with a whole lot of noise, if you haven't caught it, it will weight it at a much lower level than if you don't use that. Let's talk about how we combine variances. And this is for additive only. again, I don't want to put you guys totally to sleep. There are a whole bunch of these for multiplicative and division and things like that. These come from something called the error propagation, the error propagation equation. And what we're trying to figure out is if we have a weighted signal where the signal is equal to the sum of a bunch of weighted values, for statistically uncorrelated signals, the total variance is just the sum of the individual variances weighted by the square of the weighting. So the total variance is just the square of the weights times each individual value, and we sum them up. And so if for the weights are all equal to 1, just put them all equal, simplify everything here. We can calculate how the sigma adds up. Well, the sigma just adds up as the sum of the variance just adds up the sum of the variances, and so the sigma adds up as the square root of the sum of the sigma squared. Okay, and this is called adding in quadrature, and I'm sure you guys have seen this in various places. This turns out to be very important. This is the way that you can add the uncertainty in various noisy signals that you are adding together. And I want to emphasize this does not apply, this same relationship does not quite apply. The scaling's a little different if you're doing multiplicative or you're doing it by division. So just be a little bit careful. You need to look at the relationship that comes from the propagation equation if you're going to combine variances when you're multiplying things. Pixel Insight takes care of that for you. So when we combine images, and this is where this is relevant, for images with the same exposure length and hence noise, when we combine these images, again, the sum of the variances is equal to n, just n times the individual variances, and the RMS is just equal to the square root of n times the individual RMS. So doubling n, doubling the number of exposures, doubles the signal and increases the RMS by 1.4. So the signal to noise goes as the square root of n images that you take. And we all know this. If we take more images, we increase the signal to noise. So if we want to increase the signal to noise by 1.4, we can double the number of images. Doubling the number of images increases signal to noise by 1.4. If we increase the signal to noise by a factor of 4, we double the signal to noise. We can also look at, when we do this, we can look at the rate of change of signal to noise. And that's just, if signal to noise is just the square root of n, the rate of change is just the square root of n minus 1. And we can plot that. We can look at the rate of change in signal to noise with the number of images that we take. And so if we look at the number of exposures, and we look at how much is the signal to noise, how much improvement are we getting, you can see in the first, say, 40 exposures that this signal to noise is really improving considerably. And if we go from 40 to, say, 100, it's kind of marginal. And much past about 100 exposures, it's not very high efficiency. We've really got to work very hard. This is just the rate of change of how the signal to noise changes with your number of images that you take. And this has just come straight out of the statistics of the way we gather data. So, if you're knocking yourself out to get, more than 40 images, you really got to go probably double that to really see an effect up to 80. And once you get past that, it really gets a little bit nutty. You can do it, and guys do it, but it gets really, you enter the realm of diminishing returns. One of the things that's really important to understand about all of this is that in terms of dealing with the noise in a signal, that subtracting is exactly the same as adding. So when we subtract two signals, when we calibrate an image, that's where this counts. When we subtract unwanted noise, unwanted signal rather, noise is added in quadrature. Okay, you guys still there? Adam?
Yep.
Okay,
yes,
just checking. I want to make sure I'm still connected and that I haven't put you all to sleep. Okay, so we want to make sure that you understand when we calibrate our images by subtracting, we're adding noise in quadrature. And this is particularly troublesome when we subtract small signals such as dark and read noise, because these occur both in the data and in the calibration frame. So they're double contributors. Okay, got that? So if we were to just do single frame calibration, dark subtraction, like you do in your camera, subtracting the noise will produce, from one sub, you'll end up with the square root of 2 times the dark current. That should actually not be squared. That's a goof. Is equal to 1.414 times the dark current. So that removes the dark signal, but it increases your noise by 40% when you just use a single frame. So if we can use this knowledge of our this knowledge of how the statistics work to look at what does it take to add less than 10% to the noise when we're calibrating. That's really what we'd like to do. So how do we do that? Well,
John?
Yeah.
We just got a question that may kind of be related to that slide by Jeff Voigt. So in my red zone sky, where exposures are limited to 60 seconds and less, I'm stuck at 40 minutes total time, question marks. That's a question. Is he stuck at 40 minutes total time in 60 seconds exposures? And I think that's kind of addressing maybe even the prior slide with the graph where you're approaching little gain. But go ahead and do that whichever way you can.
Yeah. We're going to talk about how all these add up in just a little bit, and I'll make a comment about sky fog here shortly. But sky fog is one of the larger contributors to noise. And so sky fog will indeed place a very big limit on how low your background can go. And I'm not actually going to do that full calculation for you guys, but indeed that's one of the larger contributors. And so you know, going beyond 40 frames when you've got a lot of sky fog is probably, it's not going to, you may have to go a long ways beyond that to get to the same effect as a really, really dark sky. You have to go through that calculation of the sky fog, and I'm not prepared to do that here. So that's a little bit of a fuzzy answer, but that relates more to how we add up all of those errors to look at the equivalent signal to noise between a dark sky and a sky with some sky fog. So that's a little bit hard for me to just give you a really crisp answer to. So let's go back. Let's continue along with this crazy thing of trying to figure out how do we only add 10% data when we're stacking dark frames. And what we can do, the question that we want to answer here is there a way for us to use more dark frames than just a single dark frame for each image in order to calibrate the image? So if we assume that we subtract a stacked image of dark frames from each of your images, I should say a stacked data frame of dark data, or a dark data frame from each image to remove the dark signal. The way we can do this is we look at the dark signal that's inherent in each dark frame, call that sigma sub d, and we let the average, d sigma sub ds equals sigma d times the square root of m. In other words, we sum up dark noise in a stack of m dark frames. So in other words, let's just say for each image that we have, we're going to stack up, say, n or m dark frames, okay? And if we let sigma prime d equal the average value of the stacked noise. In other words, what we've got to do if we use 5 dark frames, we've got to divide it by how many, we've got to average that back down. We've got to divide by m, and that's what we're doing here, okay? So the total noise in the calibrated image will just, and again, this is just the same statistics that I've been talking about. The calibrated image is going to have we're going to just add in quadrature our noise, which is the noise from the dark frame in the very first image, in our basic image, plus this dark frame, which is from a stack of dark data frames. And the way we get that, that's sigma sub d, and we're going to square that. So we're going to get sigma sub d plus, well, what is this thing, this sigma d? Well, it's just sigma ds over m, and ds is just sigma d over m, so we can reduce that to that quantity right there, square root of m over m sigma d, and all that's got to be squared because we got to add in quadrature, and that reduces to sigma d, the amount of dark current, or the noise in the dark current, times 1 plus m, where m is the number of frames that we're taking to calibrate our darks. So if we want to make sure that our data is within 10%, our dark calibration data doesn't increase by more than 10%, we've got to make sure that this variation in our calibration is less than 1.1 of our dark data. And so if we solve this, it turns out that we have to stack up 4.76 frames, but we don't want to use 4.76, so m is an integer, so we've got to have m is equal to 5, and that leads to something called the rule of 5. So in order to, what this works out to be is that in order to add less than 10% noise during calibration, you've got to use the same exposure for your darks and use 5 times the number of data frames to compute the master calibration images. And that'll guarantee that you're adding less than 10% to the contribution that comes from your dark data. Now that's also true for read data. I've just focused on dark here as well. You could use more, but 5x is a lot. Okay, so say you have 40 frames of image data, and you want to use 5x that amount. You got to take 200 frames of dark to get that contribution down to be less than a 10% increase. Okay, so this just all comes from the statistics of the way we're adding the noise sources together in quadrature. And here's this kind of comes back to the question, which is don't forget common sense. You know, work on the biggest sources of noise first. For example, sky fog. If that dominates the signal, minimizing the noise from smaller sources such as dark current yields little improvement. Now, it is possible to show that if you use enough data, you can indeed get the signal to noise to be comparable to a darker site. But I'm not prepared to go through that whole calculation here. We'll have to maybe have another session on that. But it's a bit of a more complicated calculation, but that is possible. But in general, you want to try to beat down the things that are the largest. And in fact, when you start looking at what does it take to beat down sky fog from your backyard, the answer is it probably takes less time to drive out to a dark site and take your data than it does to take all the data that you need in your backyard to get an equivalent result. Of course, if your camera has very low dark current, using dithering with filtered spatial averaging can remove most of the significant effects and add 0 additional noise. And so that's one thing that you can do to combat dark noise. That doesn't, of course, help you very much with read noise, maybe a little bit. So let's talk about filtering and dithering real quick. We're just about coming to the end here. This relates to how data sets correlate between multiple sets and with itself. And I'm going to run through this pretty fast because this is right on the edge of statistics. But if dithering is large enough to make the signal randomly related, all the rules we've discussed still apply when we're doing averaging. And so we'll also talk a little bit about filtering, a few other useful functions, averaging, media sigma, and Winsorized sigma filters. So what is correlation? When we talk about correlation, a correlation function or parameter just describes a similarity between two functions. And I picked the simplest thing I could do in Excel here, and that's just a couple of cosine waves. And clearly, two cosine waves of nearly the same frequency correlate very well. They're almost the same function. So these correlate well. If you take and set up a very high frequency cosine and compare it to a low frequency cosine, those functions don't correlate very well. And excuse me, the correlation function itself is actually a function. It's not just a parameter. You can define a correlation parameter as well, but the correlation function is defined as something that looks very much like a convolution. You take one parameter, one function, and you take another function, you slide it over all the space and figure out the product at each position of where you slid it to, and calculate the sum. And I'll show you what one of those looks like in just a second. But if I just set the parameter 0 and look at the unnormalized correlation function, we get 52 for this first function I showed you, and 1.55 for the second function. So there's clearly a much bigger correlation number here, and these are unnormalized. I just sort of did this for illustration purposes. The autocorrelation does the same thing for itself, okay, and it's a function of distance in 2D it looks like this, and this is kind of a big complicated thing. But it's just doing the same thing. It's a little bit the same way a MTF is calculated, although that's not done with an that's done with a correlation, which changes some signs and things. But It's the basic same idea. You take a function, you take itself, and you slide it over itself and calculate the product between the two. And this function always has a maximum when the two functions align, so they're aligned at 0, and we normalize that value at 1 right at the origin. And the distance where that value falls to 0.5 is called the correlation distance. And that's kind of considered to be the distance over which you have to move your data so that data inside doesn't correlate with itself, so that for an unpatterned signal in the image, the data is uncorrelated or random past that distance. And that affects dithering. And I know we kind of talked about this on Cloudy Nights one time, but what you want to do when you dither is you want to dither at a value larger than the autocorrelation distance for any given sensor. And that can remove fixed pattern noise with the appropriate filters during stacking. And you don't add any noise when you do this. The problem with it is that the autocorrelation distance for some sensors may be too large to remove if the fixed pattern noise is big. But the good news is that for hot and cold pixels, those are typically dead pixels or active pixels. It's usually 1 or 2 pixels right in a little cluster. They're very tiny, so it doesn't take very much dithering at all to get rid of those. And I know on my camera, hot and cold pixels are probably the #1 problem that I have. So I don't have to dither by more than just a few pixels, 5 or 6 pixels, to get a very, very good result. And this is what an autocorrelation looks like. This is on the left here, this is a huge amount of random noise. And there's a small periodic signal I stuck in here to kind of synthesize a fixed pattern noise. And if you take the autocorrelation and compute it, you get this delta function. It's a little hard to see. It's a black line there with this sort of noisy cosinusoidal pattern that's in there. That's the fixed pattern noise. So that's what an autocorrelation function can do. It can kind of dig that out, but it also tells you how far do you need to move in order to average out all this random noise spatially. Okay? So, and I should mention, I discovered the last couple days that the autocorrelation is pretty easy to compute in PI, or it should be. I didn't quite figure out how to do it. There's a few little issues, but it should be easy to compute this in PI and get a really nice result. Statistical filters, you guys, I think, we've talked enough about what these statistical filters are, an averaging filter, median filter, and these last two we'll talk about very briefly. They're super easy to understand, the sigma filter and the Winsorized sigma filter. These can be applied over time, and we know that when we stack data, we have our image stack here, we can filter the data through to the output. We can also take these filters, the average filter, the median filter, Winsorized sigma filter, and apply them over space. So we have some kernel that we move around the image, and we filter the image for post-processing. So these filters can be applied both over time or over space. Typically how it's done in X and Y is we convolve. This, I mentioned that word earlier. We changed some signs here, but basically all we do is we take one function we call the kernel, this g of x, and we multiply it over space by the image, which is this f of kg. And, excuse me, typically the kernel is an even function and it's non-zero over odd dimensions. So you'll see when you do this kind of filtering that it's a 3x3, a 5x5, 7x7, etc. And they can be, some of these things can be implemented more efficiency in other spaces like Fourier methods and that sort of thing. I'm not going to go into any of that. I just wanted to mention that. The way I'm describing doing it with this equation up at the top is actually a very computationally slow way to do it. And it's often not done this way, but it is an easy way to understand it. So an averaging filter, the way it works, here's our image right here. This little green thing is what I call the kernel. That's just the 3x3. And so we set the 3x3 kernel down, and notice it's filled with 1s. So if we take each one of the values in the image data, in this case 0 multiplied by 1, and add it to the next one, and we just go through this whole thing, we form a result that we put at the center of wherever this kernel sits, and we calculate that number. And then we take this whole thing and we move it over 1, and we do the same thing, and we just gradually fill up this whole array with an average result. And I did that in Excel. Of course, I didn't want to use too high a resolution or I would have blown up Excel, but I did this with, here's this data that's really, really kind of choppy, and if you run a 3x3 averaging filter over it, you can see what it does. It smooths out the result. And we all know if we use an averaging filter, it smooths everything in its sight. And in fact, that's one of the problems with the average filter. It's it's really good for doing temporal averaging through the stack. It's preferred over other algorithms, in fact. And particularly preferred if you use noise weighting, as we talked about. But spatially, it has some problems. You notice it has edge issues. Back up here, you notice we didn't fill out these edges all the way around here. We have to come up with some tricks to fill up the edges. It also rounds out sharp edges. If there's a sharp edge in your data, it rounds it out, it blurs the result. It's generally a pretty poor noise filter. You really don't want to use it for that. Median filtering is a step up. It works like an average filter, except that instead we find the median. So we take that kernel, we find all the values, we find where half the data is above, half's below, we find that value and we put it in the middle. We don't use it for stacking. It turns out it's not as robust as stacking for the average filter. PI, PixInsight actually does have a median stacking filter, but it's not as good as using averaging. The advantage of the median filters, it does for an XY filter, for a spatial filters, it does preserve sharp edges. It does preserve lines, and it can run off the edges of the data, but it still tends to blur the image. So it's not a great filter for that either. There are lots of other good filters that we use that are typically wavelet filters and that sort of thing. But I just want you to know how these work. A sigma median filter is the exact same thing as a sigma filter, except what we do is we compute the histogram over the data, over the kernel, and we remove the data outside the high and low range. So if we were to do a plot of what's in the kernel, now obviously it's not going to be this nice smooth thing, it'll be a little choppy, but we can compute the sigma level of this, and anything, and here's a plot, sort of an ordered plot of the data, say through a stack. If the data is outside of this range, the median plus the high sigma, then we just toss it out. And then we recompute the median of this newly modified data. And that's what a sigma median filter is doing. And that's actually a very robust filter for doing stacking. And if you ever have problems with the Winsorized filter, go back to the sigma median filter. And there are some cases, which I won't go into, but where the Winsorized filter can cause problems. But this is a very robust filter. In some cases, it's not quite as good as the Winsorized filter, but the thing here is we're throwing out outliers. That's one of the good things. It removes the effect of bad data points. That's what's really good about the sigma median filter. It preserves edges just like the median. It can preserve fine detail, but it can also have trouble with wide variations in spatial noise as it moves around the image in the spatial sense. So, you know, for bright areas, it may start messing things up where you don't want it to filter as much. So that can be a problem. When we get to a Winsorized sigma filter, we're computing the histogram of the data over the kernel just like we did before. But instead of throwing out this data that sits outside of the specified range, we replace the data with whatever was the last data point in that ordered set of data. So you can see here the red points are how we would replace these two bad ones at the high end, and at the low end we'd have 3 that we would replace. And then we go back and recompute the median. And so what we're doing here is instead of throwing out the data that's outside the range, we're kind of guessing at what the data should have been. We're assuming that that data outside of the range was somehow bad. And that may or may not be right, and sometimes the Winsorized sigma filter can compute some problems, can generate problems in a stack. And so, as I say, if you see problems, particularly on very bright stars, it can create some little problems right at the top of bright stars. Go back to the sigma filter. But in general, this works really well. And at this point, I think I probably put half of you guys to sleep. Hopefully not. I think, you know, there's a lot more to this whole business of statistics. As you know, the question about the sky fog is really a good one. But we probably spend half of our time trying to solve that without these basics. So these are just the basics. That's probably enough of an intro relative to astrophotography. So I'll throw it open. If you guys have questions, I'll do my best to try and answer them.
Hey, John, have you looked at the linear fit filter?
I know what the linear fit filter is, and I have looked at it, but I didn't want to get too detailed on exactly you know, what going directly into that. So I didn't talk about it.
Okay.
Yeah, I mean, that's an interesting filter. There's no doubt about it. And in fact, a lot of these filters that are in PixInsight, as you know, David, I mean, the documentation is superb in PixInsight now.
Yeah, it is
In the
very
early days,
fantastic on their site.
Yeah, in the early days, it wasn't so good, but now it's just...
Oh my, did we lose them?
You know, I think they do a really, really nice job of that. You can take a look at it, and it's just fantastic. So,
John, Alex is asking...
any other questions?
Yes, Alex is asking, can you make suggestions as to which filter you would use for, depending on how many subs you have? I know...
Yeah, that's a good question. Yeah, well, I will just tell you what I do, and you know, maybe David may have a better answer to this. I always use Winsorized Sigma unless I run into problems with the really bright stars, and that happens every once in a while, and I'm not quite sure why I get the problems with Winsorized Sigma filtering. I know Vincent Perez in his course, he talks about it, and that was what really gave me my first clue that maybe you need to try a different filter if you have troubles with the really bright stuff. But you know, that's Winsorized Sigma for almost everything. I don't worry about it.
Yeah, you know, Alex, the PixInsight documentation for their image integration covers that pretty in a lot of detail. You know, in terms of how many. If you only have 5 frames, maybe you shouldn't even be using, you know, a Sigma clipping. You should probably be using percentile clipping or something like that, right? So they have a lot of detail in there about what's generally good for different scenarios.
Right, I know when you're using the basic pre-processing script, if you're not using the one that they think is best, they'll tell you and suggest which one you should be using. Yeah,
that's all a good point. You know, I don't think I ever stack anything that's less than probably 20 frames. I mean, I never try stacking anything really, really low, but that's a good point.
Yeah, I think remember correctly, PixInsight's documentation says under 8 subs is percentile clipping, and 8 to 30 is Winsorized Sigma clipping, and above 30 maybe linear fit. I think that's how it is. I'm not quite sure about the 30 or above for linear fit, but cool presentation. Guys out there in watching the stream, you guys are welcome to ask your questions. Oh, I got one here. From Dylan, when stacking a nebulosity, he uses standard deviation as the stacking algorithm. This gives some options like 1.25, 1.5, 1.75. Can you explain what these might be, the difference between these options? Is it throwing away more data as the standard deviation value is increased?
Yeah, I'm not so sure. I don't know exactly how nebulosity works, but I would assume that the larger that the number, the more data you're keeping, because it's telling you the range that you're saving about the mean. But maybe somebody here uses that program and can tell me I'm wrong. But that's what I would guess.
You're exactly right, John. Yeah, the lower number will toss out more data. It's a straight Sigma combine, right?
Right.
So it's a standard Sigma filter.
Thank you, David.
Okay. It's really cool how statistics applies to everything. I have people, whenever I come across a student that's taking statistics or majoring in statistics, I always ask them what they're doing with it. Because you can literally do anything with it. If you like baseball, then you can get a job with a baseball team just working their statistics. It's so unlimited. If you like gambling, you can figure out exactly how much money you're going to lose per hour you spend in the casino.
I understand that there's a business open right now called a presidential election.
Yeah. I didn't want to talk too much about politics, but yeah, you literally...
There are a lot of outliers in this one.
Well, I almost put up a table. I just came across the data for helicopter EMS accidents as a function of time for the last 20 years. And that's a perfect application for Poisson statistics. You can predict the probability of how many accidents will happen this year. It's a very straightforward application.
Another question, presuming a dark sky site, would you try to go as long as possible, say 20 minutes as opposed to 5-minute subs? John, if you want to answer that, I think a few of us could answer that, but if you want to answer that, go ahead.
Boy, I don't have a real clear answer about that. I mean, I used to think that the best thing to do was to take the longest sub you can, but of course, you have a lot more odds of having something go wrong with your mount or your guiding, or even seeing starting to get bad during the sub. These guys who are doing these really short exposures and getting thousands of images, getting pretty nice results, and minimizing the possibility of having something happen during any one frame. You can throw out the frames where something bad happens. So, statistically, I'm not completely sure that there's a big difference between the two. But you guys may correct me on that. So, yeah, I mean, I don't think either way it matters, to tell you the truth. I think it's just a matter of time. How much time do you put in?
Yes,
Well, I think the read noise may play a game here. If you have a lot of read noise, you don't have to use short frames, because every time you add noise, and the same amount of noise, because it's not truly noise, right? It's charge injection on the image. So you need to watch that level to decide the minimum frame exposure you may want to go with.
Well, so let me ask you a question, Gaston. So you have read noise, but you have an awful lot of data frames. You can average that read noise way down with the number. It goes to the square root of n. So you can average it way down if you have enough frames, right?
Well, I think it's a matter of definition, because read noise may be just a repeating pattern. I mean, at least in the application I had to deal with that before, is charge injection every time you read. And those have some fluctuation, but they are not totally random.
So you dropped out there, not what?
I said there are fluctuations, but they are not totally random from frame to frame.
Ah, well, then that's a huge problem. Okay, so that's a huge problem. If that's not the case, then you can't remove it.
Yeah, you're integrating your noise. So
the other thing that we talk about with that also is that a lot of the guys like to go after very faint targets, and sometimes you're only getting a handful of photons in a half-hour sub, and if you're not getting that long sub, then you might not get any photons to get above the read noise. And so if you're going after fainter targets, then you really do have to have the longer shots, otherwise you're just never going to see the data.
Well, that's true. I agree with that. I mean, if you're going after something so faint that you're not getting the signal, you won't see it. So I agree completely with that.
yeah, and dark sky sight is, in some sense, is similar to narrowband filter, or using a narrowband filter, and you're kind of running up against that same thing where it's read noise. And I always think of it this way: let's say the read noise is 5 electrons, and let's say your target signal is 1 electron over whatever period of time. Let's say your target signal is 0.1 electrons over that same period of time. Well, you're integrating those 5 electrons if you're not able to remove them via calibration. So it really I think it's it becomes kind of a factor where you're it ends up taking longer. Well, it ends up taking more time in effect to get it out. But I don't know if there is an actual inherent limit to what you can get out of that. I've been told there isn't an inherent limit to the ability to pull out a dim signal. One of our friends on Cloudy Nights has said that a few times to me, and I've never really been able to clearly answer that question for myself. If you've got 5 electrons of read noise and you've got 0.1 electrons coming in, or whatever represents 0.1 electrons per photon, then can you get that out? Does time fix that, or no? Does it not?
Well, if it's coming in on average 0.1 each time, the fact that on some of them you miss it, that just means on average, on the next one you'll get 0.2 electrons on average. So there I think is a lot of reasoning behind those people that take thousands of exposures, and I've seen people take RGB images from light polluted areas by using those techniques. Just take hundreds and hundreds of sub-exposures, and yes, you're getting read noise, but in each of the images, you are still getting just an ever so slight amount of signal noise that you really wanted.
Well, there is a limit. There is a limit you need to remember we haven't talked about, but it's quantification of the signal level. There is an ADC converter who take the data from the sensor and translate it in a digital number, let's say 16-bit usually. Well, if your signal is below the quantization, every time you take a frame too short, you never get anything.
Yeah.
Eventually, if you are below the quantization, you doom.
That's a great point. Yes.
So now I don't know if
of unity. Principle.
You're breaking up.
You guys are too. I don't. Maybe it's my connection here. Can you hear me there?
Now we hear you.
Okay. You can pull a small signal, out of a data set that is dominated by noise. And so it's important to understand that the signal doesn't have to be very much bigger than the total noise signature to still pull it out.
Okay. Yeah, I'm not sure if you're still talking, but you are chopping up again. Yeah, that's a great point about the quantization, because the sensor doesn't really deal in, it pretty much deals in integers at that point, and if you're below that integer, or it doesn't round up.
But there are applications. We use that in the field where I'm working, where you can do dithering type of approach in a signal level. You know, John talked about dithering, the spatial dithering, where you move the target to deter the spatial noise with the automation function, like hot pixels. But you can overcome some of the quantization limit if you are below the quantization step by adding some noise inside the electronics, such you move the quantization threshold randomly, and you create some level of dithering, which means eventually you cross the threshold of the quantization step time to time, and eventually you can improve your SNR by averaging, because this time you get a signal time to time. If you never get it, I think all the camera I know on the market for astronomy have just a standard ADC. So if you are below that, which is very dim, right, to be honest, if you are below that in the dark part of the image, because you take too short exposure, you will never get anything, even if you wait 1,000 years of integration, because any of the frame doesn't have the signal.
Well, let's get back up to like Bill Clugston's question here. Because this is all very interesting, of course, and we do that sometimes, guys. We got to watch out for that. Should he be taking 20 minutes or 5-minute subs? And my answer to that would be to, if you're at this level and you want a good practical application, a number of programs do have an exposure time suggestion. I know you can get that in SGP. I think that there's a suggested time exposure in PixInsight, and the one that's very easy to use, and you can find this in various places. CCDware has one, and what's the other one? Starizona has one, where you take a calibrated picture and you find out what percentage of the read noise is coming from, well, what percentage of that picture is coming from read noise and other sources of noise, and you specify just how much of your picture, your whole set of data, should be read noise, and it will calculate for any given sensor about how long that should be. If you could take 20-minute subs as opposed to 5-minute subs, as John has pointed out, watch out, that satellite might come through, which is not a disaster, but the doggy might kick the tripod or any one of a number of other things during that 20 minutes, and you've just wasted 20 minutes. On the other hand, at 5 minutes, it may not be, it may not be ideal. So what the philosophy behind those calculators is, you take a long enough exposure so that the read noise is only 5% or some small number like that of the total image coming through, your total data coming through, and then you stop and you start another exposure. You have to be a little careful with that. That's a real good thing for like galaxies and nebula. Watch out if you're trying to take the double cluster with that rule, or the center of the Orion Nebula with that rule, because high contrast objects or stars may be blown out by the time you get to that 5%. So just keep that in mind.
Yeah.
That's my advice.
Yeah, we always ignore this, but it does depend on your goals with the image. Are you trying to pull out the dimmest, the dimmest part of the region, or are you just trying to get a galaxy? Now, we're all astrophotographers, so oh yeah, we're going after the dim stuff, but you're talking dimmer than the read noise, which is really, really dim. There's two sides of that question. We talked about short exposures and lots of them, but remember, read noise is fixed per exposure. So taking a longer exposure, if I'm only getting 0.1 electrons in 5 minutes, well then if I take an hour-long exposure, well then I'm getting 1.2 electrons. So I'm all of a sudden approaching the level where I'm kind of getting a foothold in that signal.
Most of those algorithms are really designed to try to optimize how quickly you achieve a certain signal-to-noise ratio, right? So as long as you can meet the quantization error, you can exceed that, and you can remove your fixed patterns from your image, the fixed pattern from your read signal, you can take extremely short, exposures, and eventually you will get there, but you will get there slower than if you were taking the longer exposure, right? And that's really what those algorithms are designed to do. So the point of asking, should you take a 20-minute exposure, those algorithms will tell you, the ones Alex is talking about, whether or not it is optimal to take an exposure of a certain length of time based on the sky fog limit, right?
I think from my experience, I take always the longest I can afford most of the time before I clip. Though I have a standard anti-blooming, which helps a bit. But I think the main limitation in my case is a nearby airport. I mean, Philadelphia, I need to watch the airline schedule to decide the longer exposure I can afford. Because I'm on the path of the VOR nearby, so depending on the weather, I know that's not a good night because they all come from the same procedure. But beside that, I would say if you take a target where it's not very bright, so it's not going to clean because there is a bright star nearby, I will go with the longest I can afford before maybe you have a problem from a satellite or a plane or something like that. Because usually it's better, in my opinion, to take the longest you can afford. But above some limit, the risk becomes very large to have a problem. But as John said, if you look at those artifacts coming from a meteorite or a satellite or even a plane, if it's happened to a frame and not to the next one, right, which is, you hope, it's not, if there's two planes, they don't exactly go to the same pixel on a frame. Then when you do the stacking with median or sigma techniques, you can recover all those frames. You just drop away the pixel who were touched by the plane. So it's not that bad. I think the main limitation is probably clipping, the other side of the ADC quantization I was talking about.
Mm-hmm.
But there are some very nice sensors who have this anti-blooming. But when you use the anti-blooming system, which is not perfect, keep in mind this nice theory behind what John said about linearity doesn't work anymore. Because two-thirds above the, 2/3 of the scale of the ADC not to be linear anymore with those anti-blooming chip. So they are nice to avoid the blooming, and they help you. But when you come closer and closer to the top of the ADC, you are less and less linear. This whole nice property of noise and other things averaging is not totally true anymore.
I don't know about the rest of y'all, but all the sensors I have tested lately, the manufacturers have been setting the gain so that they hit the max ADU well before they go nonlinear, right? So effectively, you can treat it as a linear sensor. You know, I tested the linearity on mine, and it's linear pretty much all the way to max ADU. It starts to taper off just at the very end as you get up there, but I wonder if that's true across all the sensors or not. I don't know if anyone's seen.
Yeah, what other sensors have you tested on? Because I did not notice that on the 683 or the 690.
So I tested I've tested a couple Sony sensors. That's been true on that. My 314, my 6120. I tested an older SBIG ST8300. Let's see, there was one other one in there, another CAF-based chip, the 6036. I can't remember which one, but someone had sent me some data for that one.
See, maybe the gain setting was off because I've actually had to limit my flat exposures to make sure that I'm in the linear region to keep it down more around like 25,000 ADU instead of all the way up where you want to be.
Interesting.
Yeah, that's an interesting data point because I've done some work on the 8300 from SBIG, the old one, and I found I had a problem of 2/3 of the scale. But the problem may become a matter how they set up the gain versus the signal of the output of the chip, right? Because the chip has an anti-blooming capability. But as you said, if they decide to map the 16-bit maximum 2/3 of the scale of the analog signal, it may be good. But my 8300 shows some level of distortion after 2/3. But it's a very old, one of the first model I bought at the time.
It's interesting. I don't know what the history of that particular one was, so it's possible that someone had gone and modified the gain setting themselves or something too.
Yeah, I've always, from what I've read, and I've never tested it, I always thought right around that 40,000 ADU is where the 8300 tends to go nonlinear, and that mostly came out with flat frames. That's where it seemed to be discussed the most. Because who's going to hit 40,000 ADU with an astrophotographer with an astro frame? I'm shooting at 3,000. My frames come out to 3,000 ADU, so. But
I would have a question because I don't know if somebody has experience. My neighbors are nice, but it's tough to tell them to turn the light off. Some understand, some don't. But from my experience, it seems the local light, coming from your house, unless you have, a flashlight near the telescope, maybe, is not the main source of the problem inside of a sky glow. I have a way more problem with a faraway town like Philadelphia than I have with my neighbor, even if he turns all his lights on during the Christmas time. So I wonder if any of you have some experience, because it seems the light close to the scope is not a big problem.
Yeah, I actually had some experience with that just a couple days ago. That I think that's in general true, unless you're pointed somewhere near where their lights are actually situated, where the light is actually entering your telescope directly, and you start getting odd reflections. So yeah, I ended up with this very interesting gradient because it was a little close to my neighbor's floodlight the other day, right? So
Well, it's a matter of air path. So for the distant town, the lights are going through an awful lot of air, and that's being scattered back into your telescope. Whereas the local lights are not going through very much air at all before, you know, it's not a problem. So you know, unless it's shining straight up, maybe, but even that's backscatter, so that's weaker. So I suspect the fact that the local lights aren't such a big problem is just due to the air path.
You mean if there is no straight light, or at least something who can enter directly the optic, it shouldn't be a big deal. But if you have a lot of air mass to create scattering, then you get eventually this light coming inside your scope because you have enough diffusion for that.
Yeah, that's exactly right. So, I mean, the nearby lights can create not only just going directly into the optics, but create stereo. If you don't have a dew shield, or you're using a refractor without a dew shield, I mean, light could reflect off of a surface back into the system. So that's probably the bigger danger for the local lights. But I think for you know, town versus say a you know, a local security light, the local security light is a short path, and it's some of the light scatters into your telescope, but not nearly as much as the distant town that's illuminating a big air path above you, and that's scattering back into your telescope.
But you're right on the dew shield part. That's why, Eric, you remember I made that extended dew shield for the Star 71. We were definitely having issues with that, where you would get some nasty-looking images until we did that.
Well, that
You know,
I use the distance between the dew shield, the built-in dew shield.
What's that?
There was such a short distance between the built-in dew shield and that front lens. Right,
I really like the dew shield idea for getting rid of local stray lights, and I try to use it, but the big problem with the dew shield for me is wind. If there's any wind, that big dew shield acts like a sail. And the amount of vibration and the guiding errors I get goes way up when I have the dew shield on there, if there's any wind at all. So I try really hard not to use the dew shield unless I absolutely have to.
Yeah, I've actually, I know John has a 14-inch SCT, and I have an 8-inch SCT, and I kind of noticed that too. The walls on my observatory just kind of cover where the street lights are, so I don't really get any direct street light. And I don't really notice a difference between using the dew shield and not using the dew shield. So, but yes, wind. That if it's windy, and well, you're not going anywhere if it's too windy.
Are we still live, Adam?
We are still live, but I don't see any other questions coming in. So unless I see something pop up, I'm just going to say next week we're going to, our presentation is on QHY Polemaster, and Warren from Cloudy Nights posts as Rigel123 he was one of the first people to buy this, and he's going to give us a little demonstration on how it works, whether he thinks it's worthwhile, and whether it really is the solution for easy polar alignment. Something I think all newcomers dread. Yeah, I haven't seen any questions come in, so guys, thanks for coming, and I guess we will see you next week. And thank you, John, for presenting.
My pleasure. Thank you, guys. Bye-bye.
Have a good one.